So for our next example, we want to parameterize this cone. I've gone ahead and graphed the cone for you. Hopefully you recognize that graph at this point in your calculus career. So again, I see symmetry around an axis. Whoops, I want my laser, not my marker. I see symmetry around an axis, so I'm going to try and use cylindrical coordinates. And I'm just going to write down everything, and instantly I see when I switch to cylindrical, z is just r. So I get z is r, x is r cosine theta, and y is r sine theta. And I'm looking to express x, y, and z in terms of two variables. So there's r cosine theta, r sine theta. Everything is in terms of the two variables r and cosine. And so the point is my parameterization is going to be r of little r and theta is just x is r cosine theta, y is r sine theta, and z is just r. And then I know my restrictions on everything. If z is between 0 and 1, that means I want r between 0 and 1. And of course, we want to go all the way around, so we want theta between 0 and 2 pi. And so it's nice to graph the bounded region that your two variables are allowed in. So here we'll think of theta, we'll think of this as the r-axis, and this is the theta axis. So r can go out to 1, and theta can go up to 2 pi, and so we just get this rectangle, and that is the area that you're allowed to pick points from. And when you pick a point somewhere here, it corresponds to a point somewhere on the side of this cone. So that's one example. Let's do another one. So here we want to parameterize the sphere of radius root 10 centered at the origin. I've gone ahead and drawn the sphere for you. Hopefully at this point in the game you're thinking, hey, I should maybe try spherical coordinates, and that is what you should do. So let's go ahead and write that down. So we're going to try spherical coordinates. And I want us to realize something, that when I'm working over a sphere, then I know that rho, which is root 10, that's constant. So that's going to knock out one of the variables. Spherical coordinates are rho, phi, and theta. Well, rho is constant, so this is going to work just dandy. And in fact, let's just jump right to it. So we're going to get r of two variables, my parametric function r of theta and phi, and I'm going to have rho is root 10, cosine theta, sine phi, and then root 10, sine theta, sine phi, and then root 10 cosine phi. So I'm just quite literally writing down the spherical coordinates to be able to describe the sphere, and I get a function of two variables which traces it out. I should tell you my bounds. So theta, of course, goes all the way around, so 0 to 2 pi. And then phi, keep in mind, phi starts here, and then you swing, and you're allowed to swing all the way down to pi. We want the whole sphere, so phi is going to go between 0 and pi. And so if you want, again, right, you're actually pulling points from the theta phi world. I'll think about theta as the horizontal axis, phi is the vertical, and so you go out to pi on the phi axis and 2 pi on the theta axis. And any point theta comma phi that you pick here corresponds to a point on the sphere over there. And so we've been able to take a sphere and sort of flatten it, right? We've captured all of this round sphere using this little rectangle in 2 space, which is pretty powerful. So let's end this video here, and in the next one we're going to look at a special case.